We are going to go over the answers and explanations to the August 2022 Chemistry Regents exam. This is part C. Part C is 20 questions. They're short answer questions. My opinion, students don't study the short answer questions enough. So I'm going to recommend, if you're listening to this video, make sure that you are practicing the B-2 and part C questions as much, if not more, than the multiple choice, which are part A and part B1. Now, the difference between part B-2 and part C is that in part C here, you're going to see information that's given that applies to whatever questions, in this case 66 through 69, and they come from different areas of the course. With part B-2, they pretty much keep the questions with each grouping for one topic. For example, atomic structure or bonding, etc. All right, with that, let's get started. So in 66, all you're doing is balancing this equation using the smallest whole number coefficients. What I tell my students is we're always going to just bounce back and forth and balance out the atoms. So I have 4 phosphorus here on the left, and I need 4 on the right. Keep in mind that you can always bring up a side that has less atoms, right? The numbers and types of atoms on the left have to equal the number and types on the right. If I just put a little 4 in here, instead of going to the answer booklet, that balances out the phosphorus. I'm going to go ahead and I'm going to move to hydrogen. We'll deal with oxygen last. I have 2 hydrogens here, and I have 4 times 3. I have 12 now over here, right? Because remember, when you put a coefficient in front, you distribute it through the entire formula. Well, I need to put a 6 now in front of H2O to balance out my hydrogens. And that means now I'm left with my oxygens. I have 10 oxygens plus 6 times 1, total of 16 on this side. And I have 4 times 4 for the oxygen because of the subscript here, and I have 16. The last thing you always do when you balance is just double check. 4 phosphorus, 4 phosphorus. 12 hydrogens, 12 hydrogens. 10 plus 6, 16 oxygens, 16 oxygens, and we're balanced. In 67, write an empirical formula of the solid reactant in the equation. For the solid reactant, of course, that's here because you have the S in parentheses. Now, an empirical formula, if you forgot, it's the lowest whole number ratio of the atoms in the formula. In other words, what can I divide the 4 and the 10 by to reduce the number? Well, the easiest one is always 2. If I divide by 2, I get P, P2, and O5. I can't reduce any more because 5 is an odd number, and lo and behold, that's our answer. The last question, 69, I'm going to determine the oxidation state of phosphorus in phosphoric acid. Now, you have to realize that phosphoric acid, if you didn't recognize the formula as H3PO4, in the passage, it says it's producing phosphoric acid, and this is your only product. In order to get an oxidation number for phosphorus, we need to look at the oxidation numbers on either side of phosphorus. You look these up on the periodic table, and they're in the upper right-hand corner. So hydrogen is a +1, and oxygen is a -2. Phosphorus has more than 1, so we're going to figure this out. All right, so here's the setup. I have the 3 hydrogens times +1, plus I have my phosphorus, which is my X. It shows up in the formula once, and my oxygen with a -2. When I look up the oxidation number for oxygen, it's a compound. Everything should add up to 0. All you're going to do is solve for X now, and of course 1 times 3 is 3. 3 plus X minus 8 is equal to 0. Okay, X minus 5 is equal to 0, and that means X is equal to +5. And that's our answer for 69. Okay, so this next reading passage and chemical reaction go for questions 70 through 73. Make sure you read a little bit at the top here about calcium oxide, also known as lime, and then we answer the questions. In 70, it says, state the solubility of limestone. Now you have to go into the reading passage, which tells you that calcium oxide, also known as lime, right, can be obtained from the heating of limestone, which is mainly calcium carbonate. We're looking for the solubility of calcium carbonate. And in order to figure that out, again, you had to go to the reading passage. Now, in the equation, we're heating calcium carbonate to produce lime and carbon dioxide. That's not where you're going to find this answer. In order to find the answer to the solubility of calcium carbonate, you have to realize you got to go to the reference tables and specifically the solubility table. Let's do that. All right, so here we are, reference table F is our solubility guidelines. This is one of my least favorite tables. Sure enough, it's going to show up on the exam, and we're looking as to whether or not calcium carbonate dissolves in water. Now, what you see on the table are ions, right? The charges. In other words, what we have to do is we have to look at the two ions that make up calcium carbonate. That's the calcium ion and the carbonate ion. And what's also interesting about this table, I'm looking for soluble. Exceptions now are going to be insoluble. And then this column is insoluble. And then the exceptions are soluble. In other words, the two inside columns go together. These two outer columns go together. Let's look for calcium ions first. Calcium's +2. I'm looking in the first column. I don't see any reference to calcium. I do as an exception, but that's calcium sulfate. That's not calcium carbonate. Now I move over to the third column. Here are carbonate ions. So carbonate ions in a compound formula are typically insoluble in water. However, there are exceptions. Exceptions are the group 1 ions and ammonium. But guess what? Calcium's in group 2. In other words, calcium carbonate is insoluble in water. It does not dissolve in water. Now, in answering question 70, all you have to say is that limestone is insoluble in water. Move on to 71. State the evidence from the equation that the reaction to form lime is endothermic. Well, if we take a look at the reaction, notice where heat is. Heat is shown as a reactant. So you could say heat is shown on the left-hand side of the reaction. Heat is being put into the equation, something to that effect. That's our evidence. It's shown in the actual equation. For 72, it says identify the noble gas that has atoms in the ground state with the same electron configuration as the calcium ion in the ground state. Well, calcium as an ion has a charge of +2. Let's go to the periodic table and I'll explain. All right, so we're here at the periodic table. I've circled calcium. Again, calcium on all the other group 2 metals want to lose 2 electrons there. That's why they all have a +2 in the upper right-hand corner. Calcium will go from 20 electrons down to 18. So let's just move backwards. And that means then calcium as an ion is going to have the same electron configuration as the noble gas argon. That is our answer for 72. You could write the name, you could write the symbol, you could write both. For 73, state the type of chemical bonding that we have in calcium oxide. Well, remember, you need to identify the atoms that make up the formula. Calcium's on the left-hand side, that's a metal. Oxygen is on the right-hand side, that's a nonmetal. So we have ionic bonding. We now are at questions 74 and 75. Again, there's a long reading passage here. What's happening is there's titration going on. That means that we have the concentrations and volumes of an acid and a base. Usually you have one and then you figure out the other. Let's go to 74. It says compare the number of moles of hydrogen ions to the number of moles of hydroxide ions in the titration mixture when HCl is exactly neutralized by KOH. Well, If it is exactly neutralized, and notice that for HCl, we get one hydrogen for every molecule of HCl, and for KOH, we get one OH minus for every KOH. It means the number of moles are exactly equal. That's all we're looking for in question 74. In 75, what you're going to do is you're going to determine the concentration of the HCl solution using the titration data. So now, knowing the number of moles are equal on both sides, we need the titration equation. That's on reference table T. All right, reference table T, we scroll on down. Here it is, molarity of an acid times the volume of the acid is equal to molarity to the base times the volume of the base. Let's copy that over. Now what I have to look for is I have to look for the molarity and the volume for the acid, which is HCl, and the molarity and the volume of the base. I like to have the students put the acid and the base formulas on either side, and of course this is MaVa and MbVb. It's just hard to type it out. All right, I just moved left to right. The molarity of the acid is our X. The volume of the acid, go back into the passage. Here it is, 20 mils of HCl, so that's a 20. The molarity of the base is 0.1 molar, and the volume of the base was 42 mils. Of course, I'm running out of room over here, just like my chalkboard at school. We have to solve for X. 0.1 times 42 is 4.2. And then to get X alone, I got to divide by 20. Grab your calculator. Always do your math with the calculator and a piece of paper so you can write everything out. So 4.2 divided by 20, and our answer is 0.21 molar. All right, 76 and 77. We have a little reading passage here of some instrument landing on a comet. Four of the organic compounds detected on the comet are methyl isocyanate, propanone, propanal, and ethanamide. And we're given the structural formula for methyl isocyanate. 76, it says identify in these four compounds the element that makes them organic. Well, organic chemistry is the study of carbon compounds. You didn't really even have to do much more than just know that or take a look at the organic reference tables, but they all contain the element carbon. For 77, write the names of two organic compounds detected on the comet that are isomers of each other. Well, if you're going to have an isomer, what that means is it's the same molecular formula, different structural formula. Let's use the methyl isocyanate as an example. If I take this structural formula, right, and make it a molecular formula, I have two C's, so C2, I have an N, I have an O, and I have 1, 2, 3, I have three H's. That would be an example then of a molecular formula. And sometimes you might see the order of the element symbols a little bit different, but I've just broken it up, or taken it down into its atoms. What I have to do for the rest of these compounds, we have to figure out what the actual formulas would be. All right, so what I did here on this word sheet is just list the four names of the organic compounds and the actual molecular formulas. The methyl isocyanate we got from the question. Propanone and propanal. Prop is the prefix for three carbons. On is the suffix for a ketone, and al for an aldehyde. Since they both have the same number of carbons, the only difference is where the C double bonded to an O comes into play. With a ketone, it comes in the middle of the carbon-carbon linkage, and for an aldehyde, it comes on the end. This is going to be our answer. Now, one other one is the ethanamide, and for this, we see we have eth, so we do have two carbons, and we have a nitrogen and an oxygen. The problem is that the hydrogens don't match up with our methyl isocyanate. Therefore, again, propanone and propanal is the answer. Let's go, though, to the reference table so I can show you where to find these three functional groups. If we scroll down reference table R, our aldehyde and ketone are right above and below one another. And down here at the bottom, you can see the amide. So here's my amide functional group and my aldehyde and my ketone. And sure enough, propanal is listed here as the aldehyde example. And for the ketone, all it's going to be is the C double bond O in the middle. So I have 3 carbons instead of pent being 5. So I'm going to cross it off here at the 3, and then I just need to add another H. They are the isomers. Now, if we look at the amide, it's a little kind of funky here, right, for this ethane amide. I have a carbon with 3 hydrogens, and then I have the C double bond O, and then the H and H. So I'm going to put it here so that this would be this second carbon, right? The 2 carbons make it F. And then I'd have my carbon with my double bond O, and then here would be an H. Again, it doesn't match the methyl isocyanate, so that is not the answer. 78 through 81. Wow, we got this long reading passage, and then which is describing this particular experiment, and then here we have a picture of a well plate with solutions and then metal strips in those solutions, and a little key over here that tells us which ones were positive or reactions and which ones were not. Let's go to the questions and see what we have here. All right, in 78, it says, using the results of the student's investigation, state evidence that the zinc metal is more active than copper. Let's go back and take a look. Now, the metal means the solids. If I look at my zinc metals, you'll notice that there were reactions with the zinc metal with iron ions and copper ion, 2 reactions that occurred. With our copper metal, it never reacted with any of the solutions. So obviously, zinc is more active. For 79, compare the number of electrons lost by the magnesium placed in the zinc ion solution to the number of electrons gained by the zinc ions. We have to have equal numbers of electrons being lost and gained. The easiest way to know what the number is, you see that zinc as a metal, nothing has been lost or gained. As an ion, it loses 2. Let's compare it to magnesium. Magnesium as a metal hasn't lost or gained any electrons, and then magnesium and ion as an ion is 2. So the number of electrons lost and the number of electrons gained is equal, and it's 2 electrons. Moving on to 80. Write a balanced half reaction equation for the reduction of copper ions. Let me tell you, students, and I'm sure yourself included, always struggle with these types of questions. If we're dealing with copper ions, we're dealing with Cu2+, it's right here. And if it's being reduced, we're talking about gaining electrons. We have then copper 2+. Now, it's going to go to copper as a solid, which anytime that we have copper as a solid, it's not losing or gaining electrons, it's a 0 for the oxidation number. So if I'm going to go from 2+ to 0, I have to have been adding 2 electrons, which are negatively charged. That's the half reaction that they're looking. Is that easy to do? Some students will find it easy, others will find it difficult, but use your words here in the sentence as your clue. And then finally in 81, it says, state why the student was instructed to clean the surface of the metal strips with sandpaper before placing each strip into the aqueous metal ion solution. Well, the first thing you might do is go back and look at the reading passage, because it might tell us. No, it just tells us that it was sanded. Well, obviously the reason why we would sand the metal strips is that we want to make sure that we don't have any other compounds or material on the surface of the metals. We want the metal that is going to be in direct contact with the aqueous metal ion solution. What happens a lot of times with metals as solids is that they form metal oxides on the surface, just sitting out in the air. And again, we want to get rid of any compounds that would have formed that would interfere with the reaction. All right, 82 and 83, we have again a reading passage here about tetrachloromethane and a table with boiling points. In an 82, it says explain in terms of, always remember that we want intermolecular forces then into our explanation why tetrachloroethene has a higher boiling point than tetrachloromethane. If it takes, or it has a higher boiling point, takes more energy to go from the liquid to the gas phase, and that means the tetrachloroethene intermolecular forces are stronger than the tetrachloromethane intermolecular forces. All right, so that's all you had to say. And in 83, draw a structural formula for 1-bromopropane. Bromo means bromine. If you go to the reference tables for organic, remember there's the 2. We're going to start here with what I call the backbone, or the propane. Prop is 3 carbons. ANE means all single bonds. 1-bromo means I'm putting a bromine on the first carbon. And it doesn't matter whether I put it up, down, or on the side. And then I have to fill in the rest of the carbons with hydrogen atoms. Now, New York State will let you get away with just putting the dashes to represent your hydrogen atoms, or you could draw in hydrogen atoms, right, where these dashes are with carbon. Remember, carbon always forms 4 bonds, so we want to fill them all in. So there's our structure for 1-bromopropane. Here are the last 2 questions for part C, and actually for the whole test. And typically they're nuclear chemistry questions. They don't have to be. They seem to show up all the time. We have a reaction. Here it's uranium-235 being split, and you see the neutron with the uranium-235, and we get the splitting going on. And it says in this reaction, the products have a mass that is 0.18 atomic mass units less than the mass of the reactants. And in 84, it says compare the energy released per gram of a reactant during this reaction to energy released per gram of reactant in a chemical reaction. The energy released per gram in a nuclear reaction, this is a fission reaction, is much greater than any chemical reaction that is exothermic. That's all you have to say. The reason being is, just FYI, right, we're losing a little bit of mass, but this little mass, because of E is equal to mc squared, makes a ton of energy. And then in 85, we have our classic half-life question. There's always one on the Regents. In this case, in August, they left it for last. It says determine the time required for an 8 milligram sample of strontium-90 to decay until only 2 milligrams remains unchanged. So we're dealing with strontium-90. We need the half-life, and we're going to go to the reference tables. All right, half-lives are found in reference table N. We're going to scroll down and find strontium-90, and sure enough, here it is. 29.1 years. Let's go back. All right, in order to figure this out, I typically set up a little table with time and mass. Now the T1/2, we looked it up, is 29.1 years, and we're going to need that, right? It says determine the time required for 8 milligrams to decay. All right, so our mass to start is 8 milligrams, and we're going to 2. Every time that we hit a half-life, the time has passed. We're starting with 0 at 8. So in other words, when 29.1 years have passed, half is still strontium-90 and the other half has decayed. So we go from 8 to 4. And then another 29.1 years goes by. So we need to add our time. So 29.1 plus 29.1, we're going to 58.2 years. Once that's passed, we've gone from 4 down to 2 grams of strontium-90 left. And sure enough, 58.2 years is our answer. Well, that wraps it up. That's part C, the end of the August 2022 Regents. If you have any comments, if you want me to do a video about a specific topic, just leave a comment below. Keep working hard, and good luck.